All right, so we have a half an hour to kind of get through some slides. Beautiful. We've been talking about Messier objects in here. This is Messier object 106. Okay, we talked about our galaxy in chapter 15, and now chapter 16 we're talking about other galaxies. But chapter 16 kind of takes it up a notch because we're also going to talk about how are those galaxies arranged in our universe. Okay, so we're going to talk about what's called cosmology. Okay, so some galaxies we see face-on and some we see edge-on. This is kind of like a face-on version. The caption says that that bright area in there actually is a supermassive black hole. And somebody in my other class said, well, how come it's glowing? You know, you say light can't escape. What is the light escaping from the supermassive black hole? And it's kind of like the accretion disk thing, where basically it's just kind of, there's a lot of things going on in the vicinity of the black hole, so it's kind of creating its own heat. All right, so galaxies. This is a famous image taken by the Hubble Space Telescope, and I don't know if you can see down here in the corner, actually that is the Big Dipper down here. You can see the bowl stars, okay, you can see the handle, and the video I'm going to show you actually refers to this. So the Hubble Space Telescope went where there was nothing, okay, and what they found was this. So those lights there are not stars, those are actually galaxies. Okay. So in this unit, or in this chapter, we're going to talk about kind of types of galaxies. There are spiral galaxies, there are elliptical galaxies, and then there are irregular galaxies. Okay. And then with regard to kind of within those galaxies, we have dwarf galaxy is just kind of a handful of stars. Okay, 1 times 10 to the 9th is 1 billion, right? And a giant galaxy has lots of stars. Yes, kind of waited for this video. So now I have our first of a few videos. I like his accent. You can get away with anything if you have an accent. Cool. Okay, so types of galaxies. We have spiral galaxies. Of course, the Milky Way is a spiral galaxy. The thing about spiral galaxies compared to elliptical galaxies is they definitely have a disk. They have a halo region, but they definitely have a disk. And we're going to see elliptical galaxies don't have necessarily a disk. So spiral galaxies, some of them we see face-on. So this is Messier object 101, beautiful spiral galaxy. This is actually the Sombrero galaxy. Now remember, that's like a proper name. And actually we're seeing that one edge-on. And you can get a sense for the nuclear bulge in this edge-on. So remember, most nuclear bulges actually harbor a supermassive black hole. Okay, our Milky Way galaxy, we think, actually is a barred spiral galaxy. So this third one up here, where actually kind of extending from the nuclear bulge is a bar of stars. Okay, and then we have the spiral, major spiral arms coming off of those. We think that that Milky Way is that way. Now, in a minute, we're going to actually classify spiral galaxies and barred spiral galaxies, but we're going to classify them according to the size of their bulge and how tightly wound their spiral arms are. And I'll go ahead and kind of give you how that works. The larger the bulge, what we're going to see is that the spiral arms are tightly wound. And if we contrast that to a small nuclear bulge, and you can get a sense for the nuclear bulge, both, I think, face-on and even edge-on. If it's small, then we have loosely wound spiral arms. So yet another type of galaxy is a lenticular galaxy. Lenticular galaxy is kind of like spiral galaxy, and that it definitely has the disk thing going on for it, but it doesn't have the clear spiral arms. I've heard lenticulars might be kind of a transition galaxy between spiral galaxies and elliptical galaxies. So elliptical galaxies don't really have a disk. They're mostly halo. And they're relatively old stars. Elliptical galaxies have kind of your old guys in them. This right here that you're looking at, the big one is Messier Object 87. Now, one of the things we've already talked about earlier, clear back in Unit 1, was that galaxies actually are organized in clusters. So this is a cluster of elliptical galaxies. So each one of those looks like a fuzzy thing. Okay, those are elliptical galaxies. Definitely don't see a disk. Okay. So this would be an example of a giant. That's a giant elliptical galaxy, and this is a cluster of elliptical galaxies. Those are relatively less common than dwarf elliptical galaxies. This is an example of an irregular galaxy. Actually, this guy, the Large Magellanic Cloud, or the LMC, actually, which to me, the Large Magellanic Cloud, they should have used the word galaxy in its name, but that's a galaxy of stars. Remember that actually that one, like the slide says, is actually a companion to our own galaxy. That was in the southern hemisphere, so I can't photograph that one. But I'd like to go see it, actually. I should put that on my list. So Edwin Hubble, and actually we're going to see his name come up here in a minute. You're going to see a photograph of Edwin Hubble looking through his telescope. But he did a lot of work with galaxies, and actually he classified the types of galaxies. But notice that he broke the spirals out into regular spirals and barred spirals. So here we have regular spirals, and here we have barred spirals. And you can see the little sub A, B, and C, okay? Sub A, B, and C, and that goes along with the nuclear bulge and how tightly wound the arms are. So here we see a large bulge, nuclear bulge, okay, and we see tight arms for the A type. And then over here we see a small bulge, and we have loose arms. Then over here, we have our ellipticals, okay? And the ellipticals actually are also subcategorized. Here you see E0, E5, and they're subcategorized with regard to being how elliptical they are, how eccentric they are, or how oval they are. So the 5 looks more oval than the 0. Yeah. Okay, so galaxies are clustered together. We can have small clusters like this one. Isn't this pretty? So this would, in this textbook, it's kind of hard sometimes to get a fix on, is that a photograph or is that a drawing? And that's a photograph of a cluster of galaxies. Gorgeous. This is relatively sparse cluster, and this would be a packed cluster. Definitely a packed cluster. Over here, to me, I maybe see a few spirals, but I definitely see what looked to me, just my untrained eye, a lot of ellipticals. So to me, there's a spiral there, maybe a spiral there, but we see kind of a lot of elliptical galaxies.
It seems like elliptical galaxies are more yellow in color.
They are. They're yellow, and I think the slide a little bit ago even said the stars tend to be kind of reddish. They're kind of older, but they definitely look more yellow to me too. Maybe orangish. Yellow. I agree. So how are we going to gauge how far away a galaxy is? And I don't think I've mentioned it recently, but it was like, there's a slide coming up to say 1924 was finally when we got a fix on the concept of a galaxy. Before that, we were like, what are those things out there? I don't know. Might just be like little fuzzy things, more little nebula, okay? So, like I said, we're kind of building up to cosmology, final answer. Okay, cosmos, cosmology. Actually, we're going to have to talk about the origin of our universe in this unit of material. So the guy on the video we just saw kind of talked about how are you going to gauge distance to things. And he talked about parallax, the whole putting your finger and kind of closing one eye and closing the other eye, and your nearby finger appears to jump, okay? But even shorter distances than that, and actually we've used that to say how far away stars are. You know, if we're here in June and over here in December, we can actually see that star move and get the parallax angle. The bigger the angle, the closer it is. Not much angle means it's pretty far away. Radar actually is where we could do with planets. We could actually send a signal to the planet and watch for that signal to come back, traveling at the speed of light, and we could gauge this and we could see how far away the planet is. Okay, but that's not going to work for galaxies. Neither one of those work for galaxies. Instead, actually, I'm going to kind of talk you through what he introduced, this idea of the candles. Remember a little bit ago you saw all those candles? Okay. So there's something called a technique that uses what we call standard candles. Standard means you know what it is. Candle means it's glowing, okay? So basically what we do is there are certain objects in the sky that we just know how bright it is. We know its absolute magnitude. We know its luminosity. So the farther away it gets, we know that it's going to get dimmer, okay? We can actually use this relationship to get to distance. Okay, so remember luminosity is like the what it's really doing. Brightness is what it appears. Apparent brightness, what it appears. So basically, the dimmer it appears, then the farther away it is. Standard candle. So I'm going to kind of introduce you to 3 different standard candles. The closer and then kind of getting farther standard candles that work at a greater distance for us. And this is actually how we gauge the distance to galaxies. So this is using the standard candle method, not applying it to galaxies yet. This is just something actually within our own galaxy. So when we talk about, remember we talked about clusters? I don't know if you remember, this is the name of a cluster. That's the 7 sisters, the Pleiades. Okay, 7 sisters. That looks like a little dipper in Taurus. It's like this big, okay? So all of those stars were born at the same time. Also in Taurus, we have another open cluster of stars called the Hyades, okay? Now, the Hyades are generally closer to us, okay? But I guess first off, what I should say is we talked about HR diagrams. This is just basically an HR diagram, okay? Whenever we talked about that line of main sequence stars on an HR diagram, those are the main sequence stars for those 2 clusters. So we can say that actually, and what your author's done is gone ahead and mark this star is compared or comparable to this star right there. Okay. Now the fact that we see this star at this brightness, okay, versus we see this analogous star at a dimmer brightness, that means that this is farther away. Okay, it should be the same. It's a standard candle. It should be the same brightness if they were the same distances. Okay, but this is dimmer. Okay, so this must be farther away. This is brighter. This is closer. So this is a way of kind of using a standard candle. What we can say is that the Pleiades are 2.75 times farther away from us, just based upon this sort of main sequence fitting. So I mentioned I think I said 1924. So 1924, we finally got a fix on how far away the Andromeda galaxy is. And we did it using a standard candle in the Andromeda galaxy. Okay, the standard candle was a specific star. Now, do you remember we talked about as a star leaves the main sequence, it goes in that giant stage? And one of the things I didn't talk about is it kind of sometimes wiggles around a little bit. It can become what we call a variable star, okay? So there are these variable stars that actually, they pulsate, but you know how I'm kind of going, what, pulsates like that? No, it pulsates over the course of 50 days, for instance, this one. Now they have different cycles, okay? They have different periods. This is a period of 50 days. Okay, so it's bright, it's dim, it's bright, it's dim, it's bright, it's dim. And I can't imagine Hubble actually looking at the Andromeda galaxy, picking out a star, and seeing it get brighter and dimmer. You're like, really? Oh my gosh. Whew, talk about watching paint dry. Okay? So the period that how long it takes to complete a cycle, okay, the period, how long it takes to complete a cycle, actually is directly related to its luminosity. So we could pick out a period of 50 days. Let's see. So 50 days might be, I'm bad at this one. Okay, 50 days might be about here, okay? It has a known luminosity of this. That's the known luminosity. We actually could plug that into that distance equation we saw a little bit ago. That would be the luminosity. We get a fix on its brightness, and bada boom, we have distance. Okay, so that is so cool. Okay, so actually, this technique has been used in distant galaxies, studying what we call a Cepheid variable star in distant galaxies, up to 100 million light years away. Now, 100 million with an M sounds like way far away, but actually, if you've been kind of looking on the internet to see how far away we can see galaxies, we're seeing galaxies that are pushing 13 billion with a B light years away. 13 billion light years away. So 100 million light years is just one. We're not quite there yet. Okay. So getting even farther would be this other type of standard candle. So it's not a Cepheid variable, but it's a similar sort of deal. Now, we talked about white dwarf supernova explosions, and they're very standard because they all deal with that 1.4 solar masses. So they're very, you just know how much their luminosity is going to be. So actually, I've got some examples here. There's 3 supernova explosions here. And here's the supernova explosion. So for instance, the way this works is you compare these two. So this is and this would be a galaxy, okay? This is before the supernova. This is after the supernova. Is that not cool or what? Okay, so before the supernova. And actually, can you see where it's getting dimmer? It's the same luminosity. It's just farther away. Okay? So the second one's farther away. And of course, the third one, I mean, look how dim that is. Maybe that. Can't tell. It kind of looks like the lower one to me, too. Look how dim that one is compared to that one. So this is even farther away. I mean, it's got the same wattage, but it's more dilute. Okay, we actually can use the inverse square law to get to distance there.
So how do they know that those are specifically white dwarf supernovas?
Well, that's a good question. They would be looking for the same things we talked about in lecture. Basically, a companion that is in the right stage, a companion star that's got to be red giant. The other thing is it's supernova, whether it's the white dwarf or the other one, basically appear and then decay over a couple of weeks. So there was no light, and now there is a light. Okay.
I guess it makes sense.
Yeah, I don't know. But notice instead of 100 million years away, this is more energetic than the Cepheid variable, so we can get up to 10 billion light years away. So there's Edwin Hubble, the whole tuning fork diagram. And actually, it was Edwin Hubble that studied this, and I'm going to do this little video to show you. But it was him that studied this Cepheid variable and came up with this 50-day period. I don't know if it was a 50-day period, but once we understood how far away the Andromeda galaxy is, things started to kind of fall in place with regard to kind of the structure of our galaxy, or excuse me, structure of our universe. Now, one of the things we need to talk about is something we've already talked about before, the fact that the universe is expanding, okay? And it's actually, remember we talked about we can think of kind of space and time as being the fabric of space and time. Actually, the fabric of space and time is expanding, okay? And that has consequences. Actually, all the galaxies, well, most galaxies, not all galaxies, are moving away from us. And the farther away they are, the faster they are moving from us. And so we've observed this redshift. Remember we talked about Doppler effect, and if something has a redshift, it's moving away from you. If it has a blue shift, it's moving towards you. And that's exactly what the redshift is. So let's see this quick video before we take a... I like what the video said, that Hubble did so much work with galaxies, studying them and stuff, and then once he had a bunch of galaxies, he actually made this scatter plot. This is the one where he said these dots now are galaxies. These dots are galaxies. The guy in the video said if you go twice as far, a galaxy is going twice as fast. 3 times as far from us, it's going 3 times as fast. And scientists who make these scatter plots get really excited when they get a straight line. Now, it's not perfect, okay, because you can kind of see the farther you get. So this would be where we are. This is the Earth. This is our galaxy. Okay, this is the Earth orbiting the sun going around our Milky Way galaxy. And then how far is the galaxy from us? Okay, and this is how fast the galaxy is moving from us. It's what we call recessional velocity. And what I started to say is the farther they are, actually you can kind of see these lines of uncertainty. Okay, they kind of start to, okay, but it's not bad. So there's a slope to that line, and some of you guys who kind of dabble in such things, actually the slope of that line gives us Hubble's constant, h sub 0. And we can use Hubble's constant, honestly, to estimate the age of our universe. And I've done it before. It kind of messes with my brain. But it's about, according to, I think it's the inverse of Hubble's constant, it gives us a value of about 13 billion years old for our galaxy. I'm sorry, for our universe. I meant for our universe. So let's take a look at this little video here. See if this helps. Actually kind of summarizes a few things. I think it's pretty cool. So the way this works is over here, basically going from left to right, that's how far away we can gauge distances using that technique. And in blue are the different techniques. So radar actually works within our solar system. Parallax works within our galaxy for relatively nearby stars. Then we did main sequence fitting for the Pleiades and the Hyades. How far away are they? Based upon, that's a type of a standard candle. And then we did the Cepheid variables. Okay, that's how they found out how far away the Milky Way, we're in the Milky Way, how far away the Andromeda Galaxy is. And then other distant standards that would include the white dwarf supernovas. You can get farther away. And then Hubble's law, you can actually get even farther away. Because the way that works is, now that you have that curve, if you have, for instance, something that is very highly redshifted, you can get the recessional velocity, and you can find it on the curve, and you can see how very far away it is. So it's another way to get to distance. Yeah. So I thought the video we watched, I think that was the second video we watched today, that actually took this expansion and went backwards in time to contract to something small. And that object was a very dense, very energetic object, actually called singularity. And I was talking to somebody in my other class about this, but I don't know what this author does with it, but I do believe in possibly multiple universes out there. I know that there are other astrophysicists that think about that too. But just as our universe came into existence or whatever, there are other universes out there. And what's between the universes? Nothing. Nothingness. I just think it is so awesome. I'll be talking more about the Big Bang actually in the next couple of chapters. But the idea of an expanding universe now, and ultimately our universe coming from an initial point of great density and great energy, that's all part of what we believe to be true about our cosmology. So I think one of the videos we watched said this whole idea of an expanding universe is pretty good if you think of like blowing up a balloon. So kind of the leftmost balloon was the smaller universe. You know, it gets bigger and bigger and bigger. And those black dots are actually galaxies in our universe. So that's why the universe, notice that within the universe, the galaxies are getting farther and farther from each other, farther apart from each other. So I mentioned something about taking the inverse of the slope of the line that Hubble drew, inverse of Hubble's law constant, and you do get about 14 billion years. That's actually the time when, going backwards, basically that balloon was the point of singularity. It was all together 14 billion years ago. So one of the battles we fight is this kind of delay in seeing light, because we've talked earlier in this course about, my goodness, if something's 1 light year away, when the light finally gets to you, that thing has aged 1 year. So let's consider looking at an object that's 400 million light years away. Okay, so we're seeing that light when it finally gets to us as that object was 400 million years ago. So if our universe is expanding, then that object, let's just call it a galaxy, is no longer there. Okay, so I think the way this works is, you know, this is us. We are here. Okay, and the galaxy we're looking at is here. Okay, those photons leave. We travel here. Its new position is here. Okay, but what we're seeing is as if it was down here. So it's no longer in its close position, it's even farther away. So I think that it's not necessarily a cop-out, but I think what astronomers do basically is just understand that phenomenon is there. So when we look at something, we know that we're looking at its look-back time, but we don't sweat it too much. There's no really translation that people do. Okay, just to realize that it is a phenomenon. But I don't know how to get around it. Okay. So, if our universe was small, 14 billion years ago, okay, and it's been expanding for 14 billion years, okay? We're somewhere in that mix. Now, the deal here is if we look anywhere, I think I did this when we started the course. If we look for an object that's 15 billion light years away, are we going to see it? No, because our universe wasn't in existence then. So we bump up against something we call the cosmological horizon. And I'm going to tell you here in a minute, or not in a minute, actually next week when we meet, we'll talk about the Big Bang, and actually there was a delay between when any energy can actually kind of find its way through the mist, about 800,000 years after the Big Bang things settled down, so we could actually see it. But there is definitely a limit to how far we can see. So this is kind of a subtle thing. I was thinking about this in my car, and I might need to do a little more looking into this. But, you know, there's the Doppler effect, you know, like I think the video did a good job. Galaxies are moving away from us. When something's moving away from us, we get a redshift in that object. Well, there's this other sort of redshift that's happening, but it's associated with the fabric of space and time expanding. Yeah.
How do we know that everything's moving away from us?
Well, not everything's moving away from us, because we talked about how actually within our own cluster. What?
Is that what you're about to explain?
No,
Okay,
no.
because this was my thought. So everything further away is moving exponentially faster. So even if we're moving in the same direction as something closer to the center, it would still be redshifted because we're moving faster than it can come close to us.
Right.
I just blew my own head.
Yeah, because what you're describing actually is important, because that means that we're not in the center of everything.
Yeah.
Yeah, exactly. There really kind of is no center.
Ugh, this hurts.
Yeah, it does. It really does. There is no center, but
Well, there is. We just don't know where it is yet.
yeah.
Or everything's moving in the exact same direction, and it's all just a dump of a wormhole.
That sounds like science fiction.
Doesn't everything sound like science fiction in the beginning?
Sometimes. But, so, I don't know if this fits into what you're thinking, but there's this other sort of redshift, and it's not because of recessional motion. It's actually because of the fabric and of space and time expanding. And actually I have a video to show you that, kind of what I mean about that. The fabric of space and time is stretching, okay? And as it stretches, and actually next week we're going to talk about microwave background radiation. And it used to be really hot. And basically you take thermal energy, infrared radiation, and you stretch it and you get microwaves out of it. So actually that's the fabric of space and time stretching. So to me that's kind of a redshift, because if it stretches, it elongates those energies. And that's like stretching on top of stretching, I think. I think they're kind of two separate types of redshift. So there's a subtle difference in the two things that are going on. And we're going to kind of leave that idea, but we're going to come back to the expanding universe next week. Kind of finishing up, talking about galaxies and how they get how they are. We talked about the three types of galaxies: ellipticals, spirals, and irregulars. And actually, I like this picture because down here is basically how old the universe was when these galaxies, when these pictures were taken. So, for instance, the universe was 14 billion years old when this galaxy was taken. The picture of this galaxy was taken. So, really pretty close to us. Remember, as we look farther back at a galaxy, we were looking at that galaxy as it was longer ago. Okay? So you can maybe kind of get a sense for that. Now, that dotted line, I don't know if you can kind of tell these, but these are the earliest of galaxies. Okay? I kind of said that 800,000, I think, anyway. There's a certain time that we can't actually see anything. But those younger galaxies look a little more disturbed, and that actually is a true thing. I got the wrong lights on. Okay, so how did galaxies form? So this talks about the James Webb Telescope. Hopefully we'll be able to get some even better pictures of galaxies and to understand how galaxies formed. We think, though, remember, galaxies are seeded with stars, so actually the universe itself had to have larger seeds, which in and of themselves had stars born. So these larger seeds were the galaxies. So as you look at kind of this box here, these are actually kind of the galaxies that are forming within the universe. So we have kind of a couple different things going on. The time of the Big Bang, basically, we think that there was a time called inflation when basically stuff went out kind of faster than the speed of light, but it kind of established itself and then began expanding normally ever since. So we think it's pretty uniform, so hydrogen and helium, pretty uniform, but it has to have little seeds that the galaxies can be formed in. So if we look at kind of the formation of the two main types of galaxies, the spiral and the elliptical galaxies, we can kind of explain their overall formation if we concentrate on two different things. One is, are they rotating? Okay, and the other is, how dense are they? So what you're looking at is the effect of rotation. So I have two figures here to show you, and in both of the figures there are a pair of types of galaxies. If we go clear out here to the end, I'll put E for elliptical, I'll put S for spiral. Okay, so if you can kind of see here, this is no rotation. No rotation gives you an elliptical galaxy. rotation gives you a spiral. Now here in a minute, I'm going to kind of change it up a little bit and actually look at maybe some interactions between galaxies to give you a spiral galaxy. But just by themselves, that's one way to look at it. The other is density. So this one looks at density. Again, we have kind of a track of the two types of galaxies. The top one is elliptical, the bottom one is spiral. With regard to densities, I'm going to go ahead and put dense up here. Dense galaxies lead to ellipticals, and I'll put sparse galaxies tend to lead to spiral galaxies. So that's a thought. But it doesn't explain everything. Bless you. So, and I have another little video to show you. But what's thought actually is, in addition to that, we definitely have galaxies interacting. We can see galaxies interacting now. This is a photograph. It's not a Messier object. It is actually an NGC object, or a pair of objects, where a pair of galaxies are actually combining. That could be the Milky Way and the Andromeda at some point down the road. Okay. So we can use computer modeling to actually kind of see, and of course it's a gravity thing and mass interacting, to actually kind of see maybe what you get with such a combination of galaxies interacting. So let's take a look at, okay, thanks. Galaxies interacting, it's called galactic cannibalism, and actually that's basically where a larger galaxy gobbles up smaller galaxies. And kind of like the video we saw that, I don't know if you catch it, but I've read that their supermassive black holes kind of combine to make a larger supermassive black hole. I think we saw in the video with Andromeda and Milky Way maybe. Another thing that can happen as galaxies interact is actually they can kind of have all at once a bunch of stars being born. Okay, create a starburst galaxy. So I'm going to I'll put this whole slide up here, and I'm going to let this guy speak to what quasars are. Okay, quasars are actually associated with what we've just been talking about, supermassive black holes probably feeding. And when supermassive black holes feed, they call that an active galactic nucleus. He said something about the redshift in the quasars. Okay, they're actually just associated with the expanding universe. They're distant objects, so. He said something about radio galaxies. So actually radio galaxies are quasars, are blazars. I've never heard of blazars. Seen at different perspectives as kind of the supermassive black hole in a distant galaxy is feeding. Yum, yum. So one more slide, and actually, two more slides? Two more slides. He talked about an accretion disk, and so this is kind of showing you, again, the supermassive black hole in the center of this galaxy down here. So here is the galaxy, supermassive black hole. Here's the jets of energy he talked about. Right here, this is actually kind of looking at stars as they orbit the center of that supermassive black hole. Getting a fix, watching their motion means we can get a fix on the mass, just like we can get a fix on the mass in our supermassive black hole. I have one more. You guys got to see this video. This is only one more slide. Okay, so this actually, so what does this do? This compares the mass of the central bulge of the galaxy with the size of the supermassive black hole, and it kind of makes sense. Basically, the larger the black hole, the larger that bulge is. Remember we said that bulge is the is large for, well, anyway, we've talked about the bulge in the center of spiral galaxies. So, okay. Oh, I guess the other thing, and I don't know if I necessarily put on a test, but I think I mentioned it before that these supermassive black holes in the center of galaxies, they think are important for the galaxy to be an entity, to evolve into, to grow up. So, all right, that's it.